Hi friends, we are back with reaction dynamics. So, in the last lecture we have been discussing this how to know the population of various J and V states of your nascent product, nascent reactant reaction product. Okay, that is nascent row vibrationally excited species. Means what is the population pattern, how to probe that. So, we discussed this not in detail, but we just give you an outline of the technique that is very useful is your palm probe technique. Okay. In this case you use two laser, two photons. One is for pumping and next is for probing. Okay. So, and so basically basically we have used this example of ozone reaction. Okay. With H nu you generate O and O2. Okay. And then, so this is your pump, and then O plus CH4 giving rise to OH, rho vibrationally excited, rho excited plus CH3. So, you use LIF for this, laser induced fluorescence. Okay. And there are certain points that one should look into, that means there should not be much delay between pump and probe, and especially when the lifetime of your this nascent species, lifetime of the species which are trying to probe. Okay. So, nascent row vibrational this state, if it is less, then it is a problem that sometime you may miss it. So, that is why pump probe gap should be, time gap should be less. Okay. Now the thing is that regarding reagents, now molecular beams are very good for cooling molecules, because it is a directed, they are not random, because temperature is a measure of mean random translational kinetic energy. So, more the randomness more is the temperature. So, if they are more directed, collision is less, then their translational temperature is less. Okay. In some cases rotational states can also be selected with the help of your palm probe method. Okay. But the point is vibrational level is very difficult to pick up, selectively exciting the vibrational level, but we can take the help of pump probe method to selectively excite certain levels. Okay. So, as an example, let us have this HOD. Okay. So, monodeuterited water in the vibrationally lowest level, V is equal to 0 plus H nu. Okay. So, you generate HOD, in the ith vibrational level. Okay. So, ith vibrational level means it is vibrationally excited. In 0 means it is having 0 point energy. Okay. Little residual this motion, but when you excite with H nu, it goes to somewhere over here, maybe like this. So, here, so it is doing maybe some motions, okay, like this, maybe translation, maybe maybe your symmetric or maybe antisymmetric. I mean this vibration could be of different types depending on which mode you are looking into. Okay, so this HOD V is equal to 0 plus H nu giving rise to HOD VI. Then using a microwave discharge, if you can generate hydrogen, I mean nascent hydrogen. So, microwave discharge generating my nascent hydrogen H plus then plus HOD H plus HOD VI. Okay. So, that will give rise to possibility is OD or OH, I mean maybe like this reaction will take place or maybe this reaction will take place. So, that is why like if this happens then this happens, then it will generate OH, if this happens it will generate OD, and of course B primed J primed plus H2 or HD. Okay. So, this can have two options. Okay. Okay, either it will approach from the side of hydrogen or it will approach from the side of deuterium to give rise to these two products. Okay. Now, what to do? As I told, as I have given you the example of laser induced fluorescence. So, you can probe this using laser induced fluorescence technique. Okay. That is, these two can be probed by laser induced fluorescence method, LIF method. Okay. And you can do mode selective reaction. Okay. You can selectively excite a particular vibrational mode with the help of with the help of your laser. So, therefore, in that case if it is a mode selective reaction, then H plus HOD with nu OH, that is fourth, okay, with the nu OH, then you will be getting OD plus H2. Or if you do other mode selective option like H plus HOD nu OD, then you will have OH plus HD. Okay. So, then if you probe your this OH or OD, okay, you will be seeing different laser induced fluorescence pattern, like for this here you may get like something like as a function of wavelength lambda. For here maybe I am not designating the exact which one is which, but this is one pattern you will be getting. But if you do the other one, I mean the mode selective one, maybe here for this one you may be getting something like this. Okay, this is the lambda side. So mode selective reaction will give rise to different reactivity. Okay. So, you can selectively break the bond. I mean you can selectively excite a particular bond. I mean this is nu OH. So, that means you can selectively break this bond. So, nu OD means you selectively excite this bond, therefore, this will be ruptured. Here you selectively excite this. Okay. And of course, with the help of specific frequency, maybe IR frequency, I mean IR laser, you can do that. Okay. you can do this mode selective reaction. Okay. So, selectively break the vibrationally excited bond. Okay. Okay. Next, we will move on to reactive scattering. Reactive scattering. So, models for reactive scattering and the effect of translational energy. Reactive scattering. Okay. Role of translation energy, effect of translational energy. Okay. Now, consider a reaction with a barrier. Okay. A reaction with a barrier such that, I mean, say deuterium iodide. Okay. Reaction with barrier. So, di H nu giving rise to D plus I. So, dissociation. What is the what is going on? Okay. Now, in this case, when this dissociates, the kinetic energy goes to the lighter D atom. Okay. So, conservation of energy and momentum is taking place. So, if you plot this like this, so this is your ground state, this is your excited state. So, this is your repulsive, this one is repulsive and this one is attractive. So, VR versus R, VR versus R. So, you excite from here to here. Okay. So, basically this excess amount of energy, this much of energy. So, this is your R d I. Okay. So, this excess energy, I mean this much is the E translation. Okay. So, this excess energy is going to your lighter deuterium atom. So, you can also vary by changing the frequency, okay, by changing nu. So, this is H nu. So, if you change this frequency maybe here, then this one will be more. Okay. Okay. So, if your E0, that is the minimum energy, that is the surmount the potential energy barrier. Okay. I mean there is a potential energy barrier. So, if your energy is just sufficient to surmount the potential barrier, maybe that is not sufficient because there is a centrifugal barrier. Okay. So, in that case only reaction is possible at low B. Okay. Now, consider an atom-atom collision reaction. Okay. So, in that case no structure, basically hard sphere. So, hard sphere model, atom-atom collision, basically hard sphere model. Okay. Now, in that case, so you have got your here atom 1, okay, and you have got your B over here. So, impact parameter B is this, and this is your, it is changing with time because it is moving this way. So, this is your R dot, and say this is your say relative. So, translational energy E t can be written as half reduced mass into R dot square plus your centrifugal energy. If you want to know more, you can consult this any standard classical mechanics textbook by maybe by Herbert Goldstein and VR. Okay, where centrifugal energy is L square by twice I, E cent. It is basically L square by twice I means it is related to your rotational, I mean total angular momentum, okay, by twice I, and it can be shown to be equal to E t into B square by R square. Okay, reaction. Now, the reaction can occur if your radial kinetic energy at the barrier is greater than 0. So, this is your radial kinetic energy. So, if it is at the barrier, if it is greater than 0, then reaction can occur. Okay. So, that means you can write your in this way, from this you can write. So, basically this one, so E t minus E cent minus V R 0, why R 0, that is at the barrier, okay. So, which has to be greater than 0, okay. So, that means putting all the possible ingredients, E t minus E t into B square divided by R, B square by R 0 square from here minus V r, which is greater than 0. Okay. So, from this we can write the maximum value of B. So, B max can be calculated to be R 0 square divided by 1 minus E 0 by E t. Okay. Now, if we assume that P b, this is your opacity function, okay, which is equal to 1 when 0 is less than equal to B is less than equal to B max. So, this is our consideration. Then cross section for the reaction sigma can be written as, so from this sigma can be written as sigma is equal to pi B square max, which is equal to pi R 0 square into 1 minus E 0 by E t. So, basically if you plot, sigma E t, sorry, E t, this is, I should write it again, sigma E t versus E t, you can write like this, it is like this. So, this is your E 0. Okay. So, this is your line of center model for the cross section. Okay. LOC model for calculating the cross section. Okay. Next, so this is with a barrier. Okay, so atom collision with a barrier. Next, look into this reaction, say O plus CH4, that is the insertion reaction. Okay. So, ion molecule reaction often do not have barriers. So, reaction without a barrier, okay. In this case, although sometime the reactants are complicated, but let us think that these are structureless atoms. Okay. So, reactants are structureless atoms, that is like a, they are like a hard spheres. Okay. So, so what is happening in that case? In that case, if it is an ion molecule reaction, what is the interaction energy? I mean, what is the interaction that is happening? So, it is a long range potential. Okay. So, long range potential for, okay. So, long range potential. So, and in this case we have to assume this ion induced dipole interaction, and which is happening at a long distance. So, what is happening, that you have got an ion, say this is an ion, okay. I mean, this is an ion, say this is another moiety. So, this ion may be inducing a dipole, maybe like if it is coming close. Okay. So, if it is a negatively charged one, what will happen, that maybe it will tend to induce a positive charge over here. So, what is happening, that you have got your maybe your ion over here, say plus charge, which is inducing. So, a dipole is induced, I mean this side becomes delta minus. So, naturally maybe other side will become, say, less, it is more negative, less negative. So, it will act as an induced dipole. So, induced dipole ion interaction. Okay. And it is a long range interaction, and generally it is written as that is r to the power 4. So, Vr goes as something like minus something k divided by r to the power 4. So, this is r to the power 4 law, but this is a constant. Okay. So, it is a negative value, which as this increases, this value decreases. So, 4th power. Okay. So, although there is no potential barrier, okay, there is no real potential barrier for the reaction to occur, but maybe there is there will be centrifugal barrier. Okay. Centrifugal barrier, I mean your V effective can be written as your Et into B square by R square minus K by R to the power 4. So, this is the type of barrier you may be looking at. So, let us see, maybe if it is a presentation, I mean we can represent the type of the barrier, I mean let us see. So, normally what is happening, that if you have your potential barrier of the form, okay, so generally your as I already told you that this part is your repulsive one and this is your attractive one. Okay, attractive one, this one is attractive and the other one is repulsive. So the thing is there are different types of barrier that I mean, let us see if we have that particular representation. So you may be, so barrier will be like it will be like this, maybe somewhere it will be like this. So this is the additional barrier. Okay, so this is because of the centrifugal force that is operative. So that is referred to here as your centrifugal barrier. So even if there is no potential barrier, but centrifugal barrier must be there. Okay, so that is why this expression, okay, so effective V effective will be like this. Okay, and next what we have to do, we have to del V effective del R, okay, that we have to put to be equal to 0. That is, we have to extremize to find out the location of the centrifugal barrier, and if we do that, then del V del R effective will be giving you like R0, that is the location of your centrifugal barrier R0 to be like 2 K divided by Et into B square whole to the power half. Okay. So doing the same procedure as we did for the earlier case, at the centrifugal barrier we require, so at the centrifugal barrier we require, at the centrifugal barrier we require that half mu R dot square will become greater than 0 for reaction to occur. So for reaction to occur, okay. So and we get the, using this condition we get the value of B max, okay, impact parameter. Okay, so plugging in this information as we have done for the earlier case with a barrier, okay, we get the expression for B max square, and the cross section can be I mean B max square becomes B max square becomes 4 K by Et whole to the power half, okay, and so sigma is equal to pi B max square, which is equal to pi into 4 K divided by Et whole square. Now if we plot sigma ET versus ET, this plot is different. So, earlier case the plot was like this with a barrier case, the plot was like I mean it's different, okay. That is sigma ET versus ET plot, it is your E0, minimum energy just to cross cross the barrier, but since there was a centrifugal barrier, so there was centrifugal barrier, so that minimum energy will not be sufficient, okay. So so you have to, that in that case it has to surmount this centrifugal barrier. So for the earlier case, only reaction will take place at low B, okay. So and this is called your this one is called the last one, which reaction without a barrier is termed as the Langevin model. The earlier one was LOC model, and this is your Langevin. Langevin-Lasva model. Okay. Next, we have to start with what is known as the potential energy surface. Okay, potential energy surface, PES, okay, because to look into the potential details of the potential energy surface, we have adapted various experimental techniques, okay, various experimental techniques to have the details of this population of various rho vibrational levels, okay, that is population of various nascent rho vibrational levels, okay. So this will give us the nature of the potential energy surface that is involved in the reaction, okay. So for means in the last two pieces of discussion we have talked about this what is happening with a reaction having a barrier or a reaction without a barrier, okay. And cross section, reaction cross section, when you plot with respect to ET, that is a translational energy, okay. So then translation energy means when dissociation takes place, this excess energy, okay, because of the energy conservation, so it is this translation energy is gained by the generally by the lighter component. So if we plot this as a sigma as a function of translation energy, then we get two different plots, that is for the cross section, and when there is a barrier, then it's different than when there is no barrier. But anyway, even if there is no barrier, the reaction has to, and in order that the reaction should proceed, it should cross the centrifugal barrier, okay. So if we and potential energy surface means most of the cases often use this potential energy diagram, say for the diatomic system, okay, VR versus R. Ideally it is like a parabola, but for explaining the dissociation of a diatomic system, this Morse function has been introduced to take into account of the dissociation limit, because if this is the true potential energy diagram for a diatomic system, then you will never reach, you will never dissociate a diatomic system, but it happens. That's why there must be a mechanism by which this does. Now generally what we do for a chemical reaction, this is your say reactant, this is a product side, and generally this is one potential energy diagram and this is another potential energy diagram. Okay. So, maybe they may be intersecting and this point is the highest point. It is called the activation energy for the forward process. Okay. So, the reaction proceeds and it goes to the activated state and then it moves to another potential energy surface, giving rise to maybe dissociated product. Okay. So, let us consider a reaction in a collinear fashion, that is HA plus HbHc, H plus H2 reaction giving rise to HaHb plus Hc. Okay. So, we would like to find out the classical trajectory of particle. Okay. So, classical trajectory of the particles involved in such reaction. Okay. So, what we have to do, and since as I mentioned earlier that for larger system quantum mechanical calculations are difficult, and since it is a hard sphere collision model, so you can nicely apply classical laws of motion, okay, for a set of few initial conditions. Okay. So, you set up classical equation of motion. Okay. So, set up equations based on classical laws, based on classical set of equations of motion of various particles based on classical mechanics. Okay. And adapt some initial condition. Adapt some initial condition, okay, which gives rise to trajectory of these particles during reaction, during the course of reaction. So generates the trajectory of particles. Okay. Now, in one case you may have two options. One is reactive collision, another is inelastic collision. Elastic, inelastic, one case you will have means that trajectories correspond to maybe reactive collision, that will lead to the chemical reaction, or maybe inelastic collision, other situation will be inelastic collision. Okay, elastic collision and inelastic collision. Okay. So, so inelastic collision means transfer of energy. Okay. So, what is happening that you say this is a simple case that HA, a hydrogen atom reacts with hydrogen molecule, dihydrogen basically, to, so this is basically an atom exchange reaction, okay, and it is expelled, this one is expelled. So, okay. So, classically we have to solve the equation Okay. So, classically you have to solve the equation, means we have to set up equation of motion for individual particles with based on classical mechanics. We have to adopt some initial condition. Initial condition could be like initially they were in this bonded distance, and this distance was larger, then gradually we will reduce the distance. Okay. So that this bond is formed, maybe it is increasing. Okay. So we generate trajectory of particles. Okay. And the two situations could be your one situation could be your reactive collision that leads to reaction, other situation could be your inelastic collision. Now, this is a representation of your 3 atom system like HA, HB and HC. Okay. This side is your energy. So, it is your this line joining the same energy contour. Okay. Okay. So, this is your RAB, this is RBC. Okay. So, AB, RAB between A and B and RBC. Okay. So, this is a contour. So, iso energy contour, and you see this value is this is your 0.3, this is 1, it is increasing. Okay. So, this is the minimum energy, I mean joining minimum energy line. Okay. Here it is more, it is still more. So, it is basically a valley, it is basically a valley. Of course, this along this diagonal. Okay. So, it will this portion, this is called the highest energy, this is the highest energy state, maybe it is the top of the potential energy barrier, which is called the col. Okay. So, what is happening that your AB and BC, so maybe it is proceeding from here to here, the reaction is going on. So, for the reaction to occur, maybe this is your progress of reaction. Okay. This is the progress of reaction, maybe this way. Okay. So, what we are doing here in the potential energy diagram, in potential energy survey, so equal energy lines are joined together. Okay. So, this is your 0.3, so this is joined together, this is another same energy value. So, this corresponds to your 0.5, this line corresponds to your 1, this is 2, this corresponds to 3. So, energy is increasing high and high. Okay. And here also energy is increasing. So, high, then lowering, this is minimum, then again it is going up. Okay. So thereby so you join the equal energy lines with equal energy points with lines to generate your contour, and this contour, it's a, and this contour, I mean this is a cross sectional view. Okay. This contour is called the potential energy surface. Okay. This is called the potential energy surface, and it's a 3-dimensional one, because you will have another this way axis projecting towards you. Okay. So what is going on here, that so this way you can generate the potential energy surface for various various reactions. It is the example which we have used over here is the simplest example of hydrogen exchange. Okay, it is a hydrogen exchange reaction. Okay, next situation is let us have situation that early barrier. Okay, this is your early barrier. Okay, the barrier is over here. Okay, so barrier could be somewhere over here. In the earlier case, the barrier is here. So, it is going this way, then again it is going on top. I mean, here in this region the energy is again increasing from here, next is still more energy, like that, energy is increasing. So, ultimately here somewhere over here along the diagonal, somewhere over here, it is it is having the highest energy, and then again it is reducing. So, when reaction proceeds maybe this way to that way, or maybe that way to this way, so it passes through a maxima and then again minima. So, that corresponds to the barrier of the process, but the situation could be that barrier could be earlier, which is called the attractive release, okay, earlier over here. Originally in the earlier picture it was somewhere over here, but it is here. Okay. So, barrier in the entrance channel, okay, and this is your translational energy. Okay. So, one means actually if you think of your absolute reaction rate theory, that one of the vibrational modes is converted to a translational mode, and that is responsible for the passage of your reactant to passage from reactant to the product. Okay. So, barrier is somewhere over here, means it is earlier, it has been it is somewhere means over here, means earlier than this point. So, barrier in the entrance channel. Okay. So, exothermicity released before AB reaches equilibrium position. Okay. So, this is one situation. Okay. So, the moment so it crosses the barrier and then it traces this path, basically maybe fragmented products, maybe this corresponds to the reaction product in this represents the reaction. Okay. But the other situation could be if the barrier is somewhere at later point. Okay. So, what will happen in that case? In that case, it is a repulsive release, okay, and barrier in the exit channel. Okay. So, this is called your attractive release. Okay. So, barrier is here at the earlier point, but if it is at later point, then this will tend to maybe this will tend to be repelled. Okay. So, it is called the repulsive release, okay, and exothermicity released as BC extends. Okay. So, if as this extends, exothermicity is released. Okay. Preferential release of exothermicity into product translation. So, anyway, so these are the two possible situations. Okay. But another point that if it is inelastic collision, means for a reactive collision, maybe for a reactive collision your potential energy surface, I mean let us draw it over here. Okay. Maybe like this. Then maybe here. So, it proceeds this way. But when it is inelastic collision, that is energy transfer, then what is happening? It is like, of course, this is RAB, RBC. So, in that case, it goes this way, then it goes back, I mean it returns, okay, and of course in a different direction. So, this is the situation for your a reactive collision. Okay. So, what we got is that we have given here a brief introduction of the potential energy surface that it is based on the classical trajectory analysis, okay, and that gives you idea of whether means it gives you the idea on the location of the barrier, and also whether it is the case of an earlier barrier or it is the case of a late barrier. And of course, when it is the case of earlier barrier, it is called the attractive release, and the later barrier it is called the repulsive repulsive release. Anyway, that is just giving you a brief idea of the potential energy surface, which is a 3-dimensional description, okay. And other things that we already have talked is opacity function, means measuring opacity function. You can take help of this laser induced fluorescence method to find out the opacity function experimentally, okay. From the distribution of the product, okay, you can in principle find out the opacity function, okay, because opacity function is a very important it is a probability function. So it is an important quantity that while studying this reaction dynamics, it is an important thing. We already have talked about femtochemistry that deals with different potential crossing and crossing of different potential energy diagrams, and how sodium iodide decomposes and decomposes to sodium and iodine, and how this covalent and electro ionic potential energy diagram crossing each other, and how to explain. I mean, we have explained why there is an oscillation in your in the observed time spectra. So that is also that already has been discussed. So anyway, so that covers most of the major portions of the reaction dynamics. So we almost have covered the portions, that is, let's go back what we should have, like let us look into the portions that we have talked about. That is we already have talked about ultra fast processes. Under that, some of the portions are common to reaction dynamics, like femtosecond reaction dynamics, that is the time evolution of the processes, and that we already have discussed. So anyway, some of the portions that we are still to, a very little portion that we have not talked about is corrosion. That is what is happening in corrosion, what are the events, events that is going on in corrosion. So maybe we'll talk a little about this femtochemistry again in connection with this potential energy diagram, maybe in the next next lecture, once its relevance with reaction dynamics, in how or maybe some other reactions, like use of photoelectron spectroscopy or other techniques, how to look into the transition state of a reaction. So maybe some of the portions which is still to be covered, that we'll discuss maybe under the heading of this molecular reaction dynamics, and maybe a little introduction of corrosion will be dealt with in the next lecture. So till then, have a nice time. Thank you.